Today we are going to talk about algebraic topological method to analyze high-dimensional data, which are more difficult to understand and analyze using statistical methods, perhaps in some cases. And the tool here is the persistent topology for high-dimensional data analysis, and I'm going to give an overview first of what persistent homology is, and I'm going to give more details on homological algebra and how it's applied. The overview you should have in mind is that data points are in some high dimensional space, and you have a cloud of information in terms of these data points, and you're trying to ascertain the structure and the features of this data. Now, there are methods such as principal component analysis, which tries to find subspaces in this data, but those methods are not robust. And as you will see, the geometric method gives you a lot more information about the data structure, and it's computable. To understand, first of all, how you begin to find a structure in data, consider forming a sphere. In here you have two dimensions, so there are circles, but you could have a sphere or higher dimensional spheres around the data point, and with a radius epsilon. So first, let's just think its radius epsilon is uniform. If your epsilon is very, very small, these data points are going to stay isolated. They're not going to intersect. As epsilon gets larger, you could intersect the data. Where the two balls intersect, you could draw a line segment. And when three intersect at some, when the intersection of three circles is not empty. So here the intersection of, you have the intersection of two points are empty. The intersection of these three circles are empty, right? This circle intersect with this circle intersect with that circle, but all three do not intersect at some subset. But here some do, and when they do, then you form a triangle, and then you fill the area, right? So if two circles intersect, you get a line segment. If three intersect, you get a triangle, and you fill the triangle. And of course, you can do so with higher numbers of intersection in higher dimensions, and this is how you construct essentially a shape of made of these higher order triangles. So you have just data points with 0 dimension. You could have line segment with 1 dimension. You have triangle, which are two dimensional, and you can have tetrahedrals, just like pyramids, which are 3-dimensional, and you can get higher order dimensions of these kind of triangles, if you like. And more formally, these triangles are simplicial. The collection of these triangles is a simplicial complex, and you are looking at sort of organizing and extracting information from these shapes as you make this epsilon bigger. So let's say epsilon is discrete, and the overview is that as epsilon gets larger, you get different kind of complexes, and you're looking for the structures that, in some sense, which I would make precise shortly, persist in these complexes. So obviously, as epsilon gets larger and you get more structures, you are able to perhaps embed some of the structures from the previous epsilon into the new one. Maybe they in a sense persist inside of it, and here you have at H0, which this would be just basically the components. Here you have the line segments, which are the H1. Here at the H2, you have the triangles, which were full. And you see that some structures persist, some components, some line segments, some triangles persist as you make epsilon larger. And of course, you have a large structure, so some line segments may persist at part of the complex, and some may persist in some other part of the complex. So you have basically a multiset here. And you can think of this as basically a kind of barcode or like feature extraction from the high dimensional data. So that's the basic overview idea. And I just went over this, right? So you have this sort of inclusions, and you have simplicial of complexes and filtrations, which give you, in some precise mathematical sense, the algebraic structures which give you the persistent module. All right, so we need to next basically talk about homology. Well, what is homology? Homology is a way of introducing certain topological invariance in a space. And we do so, it has its roots in basically triangulation of topological structures, essentially by drawing triangles, by dividing it by triangles, and see if we can extract some information from these triangles as they are transformed, in particular under what we call a boundary operator. Right? So formally, we remember we were talking about a triangle when you have three intersections, three circles intersecting, all of them intersecting and some subset. You get a triangle, you fill the triangle. Formally, these triangles are given basically by these brackets where you write down ordered brackets that you write down their vertices in some order. So here we have E0, E1, E2, E0, E1, E2. This would be this triangle, and here you have E0, E3, E2, and this would be the other one. And this sum basically is a way of saying that the complex is made of these two sections. All right, so basically then we introduce a boundary operator. The boundary operator is essentially eliminates one of the vertices, and you formally write down what is left. So here you eliminate E0, and you get E1, E2. You can eliminate E1, you get E0, E2, and you eliminate E2, you get E0, E1. Except that we also have some coefficients. And the coefficients are there to make sure that the triangle has the right, basically boundary of the triangle turn out to be a chain, basically a cycle, as you would expect a triangle a boundary to be. So here, if you drop E0, E1, and E2, you don't necessarily get a cycle. Here you begin with E1, E2, right? So you have E1, E2. This is just going counterclockwise up. Then you have E0, E2, but that's sort of the wrong direction. So you have a minus sign here, which you can view it as having flipped E0 and E2. So the minus sign says, rather than going from E0 to E2, go from E2 to E0, and that's the right direction, and then E0 to E1. It turns out the right way to make this a cycle is to look at the position. So it is the first position, and then make a coefficient -1 to that position. So this is the 0th position, and you get -1 to 0. Here is -1. Here's the first position, and you get -1 to 1. Here's the second position, you get -1 to 2. And that turns out to give you sort of the right E0, E1, E1, E2, E2, E0 as a cycle, which you can, intuitively you can think of this as the boundary. You do the same thing here with E1, E3, E2. There's a typo here, this should be E1. And you get its boundary. All right, so now I'm going to attempt to explain what happens when you look at the whole complex, when you combine, when you apply this boundary operator to the sum. Well, the boundary operator is by definition linear, and so you get the boundary of the first one plus boundary of the second one. And when you do that, when you get the boundary of the first one plus the boundary of the second one, which is, here's the boundary of the first one plus boundary of the second one, you notice that you have cancellations. Here you have minus E1, E2, here you have plus E1, E2, they cancel. So you'll end up with the other four terms. And if you look at the other four terms, here you have minus E0, E2, which means actually going from E2 to E0, right? Because there's a minus sign here, and so you get it in the reverse direction, E2 to E0. Here you have E0 to E1, and then E1 to E3, and then E3 to E2. So again you get a cycle. And what happens is that anytime you get a cycle, right, here, and you attempt to apply the boundary operator, you would get 0. Well, we can check it. So here we have, if you apply delta here again to this sum, it's as if you apply delta here twice, right? So when you do that, and you repeat this operation, you'll see that you get 0. In fact, this is the case all the time. You can prove that no matter what the simplex, the simplicial complex looks like, if you apply the boundary operator twice, you would get 0. All right, so if you apply the boundary operator to a boundary, you get 0. Is that the only time you get 0? Actually not. You get 0 in some other cases where the complex that you're applying the boundary operator to is in fact not a boundary. And to understand that, we have to look at a more complicated situation. The situation we are going to look at is sort of a triangulation of, an annulus, basically maybe a flat donut where there is a hole here. And if you, fill it with triangles, and this is how you fill it with triangles, you will end up with, so this is actually the hole, and then you have 1, 2, 3, 4, 5, 6, 7, 8 triangles filling the area, and they are all oriented counterclockwise. So I haven't written all of them here. So the complex looks like things like D, B, E, B, F, E, and so on. Now notice, just intuitively, it looks like you have this complex is bounded by a cycle here, A, B, C, and one on the outside. So let's orient them both, as we have done here, clockwise, counterclockwise. So if you have A, B, C here, and then you have maybe starting from here, D, E, E, F, and so on. So these are actually you would think that they sort of end up to be the boundary even before you do the calculations. And if you do apply the boundary operator to C, as we did in the previous slide, you do in fact get these as the boundary, but if they're both oriented clockwise as we have here, when you do apply it, you actually get the difference. You don't get C1 plus C0, but C1 minus C0. And of course, if you apply, as we discussed before, the delta operator twice, you would get 0 because it's a boundary. And so we know that essentially C1 minus C0 is a boundary, and when you apply delta to it, the boundary operator to it, you get 0. But that is not the only way you get 0. You actually get 0 if you apply the boundary operator to C1 and C0 also, even though C1 by itself is not a boundary, right? So the boundary is actually this difference. So C1 or C0 alone are not the boundary. They're not the result of applying delta to something, and you can prove that. Yet, if you apply delta individually to C1 and C0, you get also 0. So there are two kind of, if you like, closed simplices here. You have the kind which is closed because it's a boundary, and you either have the kind which is closed even though it's not a boundary. And we are not so much interested in the kind of closed simplices which are boundaries, right? So we are going to set boundaries in a way to 0. You're going to sort of collapse them and declare two chains which, for example, here the difference forms a boundary to be equivalent. And this is pretty much, it's like the mod operation, right? So what we do is we have numbers, if the difference is 5, we say that they are, in a sense of mod 5, equivalent. Because what we are interested is how they differ from each other when they are all viewed as at the interval from 0 to 5. So we think that 7 and 2, in fact, are the same because they differ from their multiple of 5 boundary by the same distance, right? So if you go from 2 to 5, you need to take 3 steps to get the boundary, if you like, which is 5. And for 7, you also have to get 7, you have to go to 8 and 9 and 10. So in fact, you also need to take 3 steps to take to each multiple of 5 boundaries. So 5 and 10 being the same, so you would say that they are essentially modded out. And here, this is what we are doing. We're going to mod out all the boundaries from all the closed chains. So we have here an addition operation here, and you have a boundary operator here. And so we could just consider all the closed chains, everything that when you apply delta to it gives you 0. What we are going to collapse and declare as equivalent all the closed chains which differ by a boundary. So C1 and C0 differ by a boundary, and we are going to say C1 is equal to C0. So they are in fact the same. And this is done by this mod operation. Now, if you're talking about, basically line segments, the one-dimensional stuff, this would actually give you the algebraic structure, which is the first homological group. And I want to go back here and tell you that Here, if you take the homological group, you would get basically a zero-dimensional object, because a trapezoid, which is shown here, doesn't have a hole here. So the whole thing is what we call contractible. Essentially can be contracted. The whole thing can be contracted into a point, and it has no dimension. While here, if you try to contract this area, you're going to end up not being able to, no matter how you contract it, you're going to have a hole here, right? You cannot collapse the hole by sort of squishing the material here, because there is no material here to squish. And therefore, you'll end up with one dimension. And so the homological group here is going to be one-dimensional. Now I'm going to go over this in a bit more details. What happens is that, you know, in the previous case, you saw that when we combined these two we applied the boundary operator and we combined them. Here E1 and E2 and minus E1 and E2 basically cancelled, because you were going in this direction here along E1, E2 in one complex, and you were going at the opposite direction, and they cancelled. So this common line segment cancelled, and you end up with this cycle. So here, when you do the same thing, these line segments cancel, essentially these cancel, and you will end up with these two separate chains as the boundary. And the basic picture is that, therefore, when you apply the boundary operator, you say look at in the vertical direction, you get these two chains, which we just said we view as equivalent. So we can actually eliminate one of them and represent the two only, say, by this chain, right? Because C1 and C0, we said they're the same, because the difference is set to 0, modded out, and therefore you can think of the difference being represented, and because C1 and C0 are the same, you could just, you know, represent it with one of them, which is I have shown here with this smaller triangle. So that's what the delta operator does. Now on the other hand, if so now we are going to, so we are not talking about a new complex. We're going to rather than increasing epsilon, we're going to go down, and we're going to get something that is of lower dimensions. If you make the epsilon smaller, perhaps this area doesn't get filled, and if it doesn't get filled, you don't have this connection. You cannot apply the delta operator to make them equal and mod them out. You would get actually two different cycles. So how do I was talking about the way of including one simple complex inside and the other and see what persists. So this is the picture of persistence here. It's a very simple one. It's one-step persistence, because you see here you had two, right? You had two cycles, and one of them collapsed. So you went from dimension 2 to dimension 1 in this direction. So the dimension collapsed, and you actually were only alive for here, and you died in the next step. In a more complicated situation with more components and so on, it may be that this collapse going from 2 to 1 doesn't happen in one step, and you persist longer. That's the idea of persistence. And if you sort of, so this is the picture we had in the previous one. Here was the delta operator, and here was the inclusion, right? So let's go back and try to remember this picture, and I'm just superimposing it here in a more complicated situation. Here we saw that we had the persistent only one step. You may have more step, and it's a more complicated definition when you get, you know, a longer bar and a longer distance between birth and death of those points. So this is in this direction, and delta, the boundary operator, is in that direction, and this essentially captures the whole picture of these bars. So in fact, what can you do? And so of course the question is, how do you, I mean, I did this by hand in a very simple case, right? By just doing the boundary operator and applying it. It turns out there are efficient linear algebraic methods to actually come up with these features at various dimensions and understand how, as you look at the data and, you know, connect the points with various sort of simplicial complexes, what happens to the structure of the simplicial complexes when you look at when you think of them in a sequence. In a way, if you change your resolution, what happens to the previous structures as you change the resolution? And that's the key information on understanding the shape of the data. And there have been very successful application in studying the shapes of proteins. The way a protein behaves depends on how it is sort of shaped, and the shape of the protein is given, for example, by hydrogen bondings. And so if you want to figure out the shape from the cloud data, this method has been very successful. Another place where it has been very interesting is in the structure of galaxies. Using these methods, you can see something that persists is large subsets of points distributed in predominantly two or one-dimensional manner. So essentially, you see that galaxies are either sheet-like, and that's sort of the structure that persists as you include more and more points, and they're also lament-shaped, essentially three-dimensional. So that's about it for this. I am